Uh, Good afternoon, everyone. We like to would like to apologize for what happened yesterday. I think it was a general problem. We thought it was a localized problem, but we are happy that today we are back on track, and hopefully uh, it will not happen again. We hope and pray for the same. Uh, So I would like to pick up from where we left yesterday, and then we will do some practical at the end of the day. So let me just try to go to. Can I see in the chat if you're getting me now? Type 1. Okay, good. So I think we are on track. So I just want to pick up exactly from I want to start from the principal component analysis. Yeah, so yesterday we were talking about data reduction or dimension reduction, and principal component is one of the tools so that is used very frequently in dimension reduction, and it's also one of the tools that is highly abused by very many people. In most cases, if you ask somebody why are you using this particular tool, what do you want to communicate? Sometimes you don't get the answer. So for the main reason as to why one can use a principal component analysis, the first one is to reduce the number of dimensions of the data set. So if, for example, you have, say, 50 variables that you collected, you can reduce this to, say, under 5 variables, under 5 principal components. And then once you produce the many dimension, you can use that information to find out if there's any pattern in the I dimension of the data. This is mainly done through looking at the principal components. If you plot, we use biplots, and from the biplots, you'll be able to see whether there's some pattern in your data set. It will also be used, also use it for visualizing high dimension data. So the whole idea behind principal component analysis is that we are creating new sets of variables, and these sets of variables are what we call principal components. And principal components are simply going to be a linear combination of the original variable that you're dealing with. So this is a linear combination of the variable that you have. So let's say, for example, this is our new variable that we want to create. We call it principal component 1 or PC1. And then PC1 is going to be a combination of all the other factors, the other variable that you measured in your study. So there's X1, there's X2, up to, say, XQ. And each of them will have some kind of a coefficient like what we have in the regression. So you can see from here, that's why we say this is a linear combinations of the different variable. So the idea here is that the new variable that you create will have. Okay. How many people are not seeing my screen? Just let me first stop the show. I want to. Yeah, I think everybody's seeing my screen, so I don't know. There are people who claim they are not seeing. Okay, good. So let me just continue. Okay. So we have this new dimension, so we have y1, we have Y2, we have Y3, and so on and so forth. So the new variables that are derived are of increasing importance, like we're saying here. So that means principal component 1 is the one that explains most of the variability in the data set, followed by principal component number 2. But in addition, also that the principal component are independent or are not correlated. So in one way or the other, they tend to give independent pieces of information. So the pieces are uncorrelated and are ordered so that the first few of them account for most of the variability in the original data set. So that's the whole idea behind the data reduction. So if you have 50 different variables that you measured, you want to reduce this to say, for example, let's say only 3 principal components. And that would be the main purpose. So we hope that the three principal components that you actually using are going to account for as much variability as possible in the study. So principal component can also be looked at as changing the coordinate system. So we have our normal XY coordinate system. So here, and when you see with our XY coordinate, with principal component analysis, we are creating new coordinates. So we are creating actually new axis. Now, as you can see, this is our first axis, which is our principal component 1. And principal component 1, as you can see, this is where you see the bigger percentage of the noise of the variability. So principal component 1 tend to explain a bigger variability in our data set compared to principal component 2. And then we can bring maybe another principal component 3 or a principal component 4 and so on and so forth. So from your so many variables, you can reduce the number of principal components. So in terms of utilization, so once you converted or you created your principal component, you're going to actually use the information to either generate a good graphical representation. That is what to say you want to have very good visualization out of it, or we can also use the outcome or the output from principal component analysis as an input in other analysis. And this is especially in principal component in regression analysis. So what we can do is then that because we have so many observations, we cannot use all of them in the regression. So sometimes you have so many observations, and the number of observations are actually too many compared to the number of units on which you made measurement. So let's say, for example, we take measurement on 50 people. So you have 1 up to 50, and then you have 100, maybe say 150 variables measured on this 50. So you can see from here that your rows are shorter than the number of columns. So in that case, this kind of data cannot be handled properly using the normal regression that we have. So the best thing would then first be to reduce the number of variables from say 150 to say 10, and then we can do regression analysis. Now, this is also useful when the variables that you're dealing with are highly correlated. Remember when we said when the variables are highly correlated, what happens? The issue of multicollinearity will come in, and the issue of multicollinearity makes the coefficients that you've calculated to be unstable. They will have a lot more variability. So in this case, we just need to get the first principal component, and then we use those principal component to do our regression analysis or to do our data visualization, rather than to depend on the entire data set that you're dealing with. Let me see if there are any questions. Are we still okay? You can put your questions in the chat, in the Q&A. If there's some other question, you can put in Q&A, and then my colleagues, Ellen, will answer them for you. Our boss is going to come a little bit late, but she will be in. So today you see, she will join at some point along the way. Okay, so let's proceed. Then the other data reduction techniques that is also commonly used is what we call multidimensional scaling. So multidimensional scaling uses the same principle as principal component analysis. That is also based on data reduction, and then it is also for visualization and other things. The main difference here is that our MDS does not operate directly on the multivariate data set itself. So what happens is that it first converts the data set into pairwise distances between the units. So if we have your data set, the normal data set that we know, let's say you picked several observations on 10 students, what it does is then it first uses that data there to come and create a data matrix. Now, when you create a data matrix, and then from the data matrix, you do the decompositions, and then you get your principal component or principal coordinates. So this one is what to call, you can have what to call principal coordinate analysis. So, and then from there, you can still do your visualization the same way you would do with principal component analysis. So multidimensional scaling aims to find a set of points in low dimension, just like principal component analysis. And then we have two type of multidimensional scaling. We have what called the classical multidimensional scaling, which is also called principal coordinate analysis. I know there is always confusion between principal component analysis and principal coordinate analysis. So I think today you'll get the clarification. Principal component and multidimensional scaling is actually useful, especially if you have some missing observations. When you have missing observations, sometimes calculating the principal component becomes a little bit challenging. So if you want data reduction, the first thing you can do is to convert your data set into pairwise distances. And these pairwise distances can then be decomposed in a similar way to now get for you different the new variables, so the principal, the coordinates, and this new variable can then be used the same way you can use the principal component analysis. So here it takes an input in form of a dissimilarity matrix, and then produce for you. Now, the difference between the classical and then the non-metric, and then the non-classical principal coordinate, principal and multi-dimensional scaling is that the multi-dimensional scaling, the classical ones, assume that the distance that you're dealing, the distance kind of matrix that you're dealing with has to follow some kind of conditions. So for example, the distance between A and B and C should add up to some value. So that's I'll ask you to go and read about the metric characteristics of the distance. But we then have the non-metric MDS, which in case it can take distance measures that are not metric. So for example, sometimes you can have distances based on judgment, my ordinal judgment, say, oh, A and B are closer together. I mean, you could have distances based on rank, based on some kind of score. If they don't follow the metric, then you can still use multidimensional scaling, but in this case, the distance there's some characteristic that does not, the distance measure that you have doesn't have to follow. You to go and try to read a difference between the classical multidimensional scaling and then the non-metric multidimensional scaling. But at the end of the day, when it comes to the interpretations, the interpretation is similar to what we have in principal component analysis. So I'm trying to build up the argument from principal component analysis. And we said, okay, from principal component analysis, you can convert your raw data into distant matrices, and then you can decompose the matrices, the distant matrices that you have, to get the different principal coordinates or principal. I mean, you could also still talk about principal component, but these are principal coordinates, and then you still use it the same way like you'd use the principal component. And then we have what we call the correspondence analysis. So the correspondence analysis is also very similar to multidimensional scaling. And that means it's also similar to principal component analysis. So here what happens is that we are dealing in this case with categorical variables. So when you're dealing with categorical variables, we all know about the contingency square. So let's say, for example, we have, let's say we have a contingency table. Okay. So we can have a contingency table of 2 factors. Let's say you have, I think I have a, okay, let me just use this example. So here, for example, you have the smoking class. So you can say somebody is either a non-smoker, somebody is a light smoker, a medium smoker, a heavy smoker. So, and then we have staff categorization. So we have senior staff, senior managers, junior managers, senior employees, junior employees, and then you have the secretary. So this is what we call a contingency table. Now, if you want, what we always know how to deal with this is that we can always go and do chi-square analysis based on that. Now, when you do chi-square, you can make a conclusion that let's say, for example, here that there is an association. Let's say we can conclude that there is an association between the smoking class and say the manager, the staff categorization. So if we conclude that there is an association, so the question that always comes in mind would then be, where is the association coming from? Okay, where is the association coming from? So for chi-square, always what we do, we calculate the expected versus observed value. So you want to see the cells where there's a big difference between the expected value and the observed value, and you try to use that as a basis to explain the association between the 2 factors, in this case, between the smoking class and then the staff categorization. So somebody may want to say, well, let me first try to clean off this. Okay, somebody may want to say, well, junior employees seems to be more in the smoking category, let's say, than non-smoking. Okay, so you can see, you can look at this as 18 versus this. You could look at the secretary as most of the secretaries are either light smoker or non-smokers. You could look at it in that form. So with correspondence analysis, what we do is then that we move one step ahead of this. So let me go back a little bit here. Okay. So what we do here is that from the contingency table, like what we saw, we come up with a chi-square test. We can do a chi-square test. Now from the chi-square test, we can construct some kind of a table, not really a distant measure per se. Let me just put it in quotes. And then based on this, we can do a dimension reduction, just like what we've done before. So always what happens in this case, we end up with calculating probabilities. What's the probability of being here if there was no independent compared to if there is dependent between the 2 factors. So we are going to construct tables of probabilities, And these tables of probabilities are the one that we are going to use to actually do a dimension reduction on. So then it will help us to have a better explanation of what is going on in a 2x2 or in a contingency table. So correspondence analysis is like principal component analysis, but now applied to categorical variable. It can also be represented in the forms of the first dimension versus the second dimension, and so on and so forth. So here, for example, you can have here this dimension, this group versus that. So if this is our first dimension, so you can see that this seems to have this category versus this category. And then if you go to the second category, we seems to have this group here. We'll have this group here versus the other group here. I'm also happy to announce the arrival of our boss. Prof, you're most welcome. Okay. So mathematically, correspondence analysis can be regarded either as a method for decomposing the chi-square statistics used to test for independence in a contingency table into component corresponding to the different dimension that you have. Or it can also be a method for simultaneously assigning scale to row, a separate scale to row and a separate scale to column. So if you go back here, you want to compare, you will be able to compare different categories of smokers. And that is, you can look at the different columns independently, or you can also look at the different rows independently. So you will actually be able to compare the different employees, and you'll be able to say, for example, that, well, we seems to have more senior employees who are non-smoker compared to other groups. So that's the kind of information that correspondence analysis is likely to give us. So it is a technique for displaying multivariate categorical data graphically by deriving conditions coordinates to represent the category on both the row and column. And then you can plot to display the association graphically. So this is what kind of what we have here. Are we together still? Hmm? Okay. And then, so I tried to build the story a little bit from the principal component analysis. We came to multidimensional scaling, and then we came to correspondence analysis. And then we are finally going to look at what called the factor analysis. Now, factor analysis has a special considerations. So factor analysis has been developed mainly in social sciences, where there are things sometimes you cannot measure, you cannot measure some certain things directly. If you say somebody is religious, for example, there are different elements of being religious. Is it because somebody goes to church or goes to the mosque? Is it because they're helpful to help others? I mean, what are the different components of that? If you say that somebody is wonderful, how would you measure somebody being wonderful? There could be different elements to that. Now, for those who work from 9 to 5, there is a common thing called burnout. So burnout is when someone who has been working very hard on a project, all of a sudden he feels that the energy is gone. So sometimes you reach your office and you find like you want to go back home, but because you don't want to be chased from your job, you will have to continue. So that's something that you hold. But you cannot measure burnout directly, but you can measure things that you can associate with burnout. So you can, for example, design a question that can help to measure motivation. So for example, you can tell somebody, can you rate the level of your motivation on a scale of 1 to 5? You can measure stress. Can you ask somebody, can you rate out the level of stress? You can find out whether somebody have new ideas or not. So we assume that these different variables are driven by the same underlying or the same latent variable, and these are what called the factors. So factors are these things that you cannot measure, but you are interested in studying. So like, for example, intelligence. Intelligence is one of the areas that use a lot of factor analysis. So the concept here is that these multiple observed variables have similar pattern of responses because they're associated with a particular latent variable. I'm going to show you an example when I go to another presentation. So we can assume that people may respond similar to questions about income, about education, about occupation. So about all this will be, all of them are measuring what we call the socioeconomic status. So if you talk about income, you talk about education, so income measure one aspect of socioeconomic status. Education would measure another one, occupation, and so on and so forth. So we need to be able to look at the data set that we have and then be able to come up with some kind of underlying variable that will help us to explain what is going on. So factor analysis has three main uses. The first one is to understand the structure of a set of variables. So this has been used extensively to understand the structure of latent variable called intelligence. So most of what we use today was developed based on that. It is also used to construct questionnaires to measure some underlying variable. So if you want, for example, to measure, let's say, burnout, now how do I construct a set of questionnaires, a set of questions that can actually measure burnout? And like principal component analysis is also used to reduce the data set to a manageable size while retaining as much of the original information as possible. And in most cases, what happens is that factor analysis and principal component analysis are quite similar to close to each other. The differences are not much, but you can also first do principal component analysis and then proceed to do factor analysis based on that. So principal component analysis is a process that can help, it's a step in achieving factor analysis. So the underlying dimension that we want to measure are what we call factors or latent variables. So the main idea here is that by reducing a set of interrelated variable into a smaller subset of smaller sets of factors, factor analysis will be able to achieve what we call parsimony by explaining the maximum amount of common variance in the correlation matrix. I have a small example that I'm going to show after this that will really try to bring this one quite clearly. Just to mention, when you're doing factor analysis can be categorized into two. We have what we call exploratory factor analysis, and then we have a confirmatory factor analysis. So the exploratory factor analysis is used in the earlier stages of investigation, and it's mainly, you can also use it to set out future hypotheses that can be tested. So with the exploratory factor analysis, we'll determine which observed variables are highly correlated with the factors. So remember, if we come up with 3 factors, the different variable that we measure will contribute differently to the different factors. So we want to see which variables contribute to which factor. So if we are measuring burnout, what are the different factors that are there in burnout, and which of the variable that we measure that let's check whether there are questions that need my attention, but I think it was okay. So here the thing is that we have the variable that we observe, and we want to relate this variable to some factors or what we have an underlying factors. So we want to determine which of the variables are highly correlated to the factor, and how many factors are needed to give an adequate description of our data set. And this is also very useful as far as constructing questionnaires are concerned. So if, for example, you have several variables that you measured, and then you come and look at them try to construct factor analysis out of the data set that you collected, you are going to realize that some questions become redundant in that they will not be contributing to the different factors that you've highlighted. So in that case, you may need to drop them from your questionnaire so that you don't go and ask your respondent so many questions that may at the end of the day not contribute to your study. So what briefly also what we can tell about exploratory factor analysis, that you don't place any constraint on which variable load on which factor. So since you are exploring, you're not going to restrict that variable 1, 2, 3 are for this factor A and not for factor 2, B, and so on and so forth. But in confirmatory factor analysis, you can actually have some constraint. So variables are allowed to relate to a particular factors while it may have zero loading on other factors. I'm going to explain what the loading is with an example. Probably this one is going to be a lot more easier. So a confirmatory factor analysis may actually arise from a theoretical consideration. So always as a social scientist or as a psychiatrist or a psychologist, you have some theoretical consideration. And based on that that consideration, you may want to actually go and test test your concept using exploratory data analysis, or you can start with the results from the exploratory factor analysis. And then based on the result of exploratory factor analysis, you can go ahead and do your confirmatory factor analysis. Now, confirmatory factor analysis is actually one of the sets of what we call latent variable modeling. So the confirmatory factor analysis model are a subset of a more general approach to modeling latent variable. And these are mainly categorized as structural equation modeling or covariant structure modeling. So these are things that we may need a bit more time to cover them. So such kind of model allow both the response and exploratory latent variables to be linked by series of linear equations. So that is an overview of the different approaches that one can use to determine use for multivariate analysis. So the main purpose of the presentation is to empower you, to allow you to have ability to be able to make a choice when it comes to analysis. And you need to know when you can use multivariate analysis and when you can use univariate analysis, but also you need to know which of the tools you can actually use. So that is the purpose for the presentation that started yesterday and ended today due to the internet failure of yesterday. Otherwise, we should have finished this yesterday. So now I want us to move and try to look at factor analysis in more detail. And then we do some, we run some R script and then try to do interpretation of some results. Hopefully, using a live example will reinforce the points. Okay, are we together? So I'm going to switch a bit. Are there questions? Okay, I thought the difference between with the PCA, principal component analysis, as I indicated, can be done within factor analysis. Factor analysis per se, the main idea behind factor analysis is that you want to actually analyze latent variables. They're variables that you cannot measure, and you cannot measure directly, but you can measure other variables, and then you can use the information from other variables to construct what we call factors. And based on those factors, you'll be able to explain the phenomena of what is going on. Okay. Now, a factor in this case, when we are talking about a factor in this case, is some kind of a conceptual idea. Let's say, for example, burnout as a factor. Let's say being religious as a factor. Variables are those questions that will measure the different aspects of the different aspects of a factor. So let's say, for example, let's say the factor is religiosity. Okay, we want to say we are interested in finding out how religious people are, but you don't have a scale on which you can measure being religious. That now becomes an underlying factor, which is an underlying variable or a latent variable, which we now call a factor. Now, things that you can measure, for example, you could say, you can ask people, how many times do you go to church in a month? That could be one. Going to church is one aspect of somebody being religious, but that can be measured directly. That's the variable. Now, you can also ask, how many times do you greet your neighbors every day as you're going? That could also be one aspect of being religious. Do you visit how many times do you visit which doctor? That would also be part of being religious. So those are the different aspects of what we measure, of what we actually measure. Now the issue of multivariate, which data can be applied to, we talk the categorical data. I think the categorical method that we talked about correspondence analysis as one multivariate technique that can be used for categorical analysis. Correspondence can be used for categorical analysis. After you've done your chi-square, you can proceed. We talked about the principal component, mainly make the assumption that you're dealing with quantitative variables. If you're not dealing with quantitative variables, you can also deal with true or false. You can construct distant measures. And then when you construct the distant measures, you can actually go ahead and do multidimensional scaling, which is still similar to principal component analysis, but now you're able to use it onto onto a matrix, which is a matrix of pairwise distances between the different observations. Different between t-test and a chi-square? No, I think that one you can go and read. Okay. Now let's have, okay, let me first continue a little bit with another presentation, and then I can give a break, then we come back and no, those are now the details or the procedures that each each multivariate analysis have a whole range of procedures. So whether you're going to do standardization, whether you're going to use correlation matrix, whether you're going to use covariance matrix, those are the finer details. So for me at this point is, first of all, we need to know, you should be able to choose the method that you want to use based on the analysis that you want to do. And then you need to know how to do, and that's where now we can go and look at in each and every, in the different method that we have. So once you choose principal component analysis, then you can go in principal component analysis and look at the steps and look at the procedure that is covered there. Okay, let me change a little bit. So the material for today has been shared. Okay. So I have one of the books that is my favorite book. There's Discovering Statistics Using R. I picked some material from that and modify for this presentation. This is the shorter presentation on factor analysis. Okay. So so this is an example that we're going to look at. Let's say, for example, you're interested in determining what makes a person popular. So there are several measurements that we believe can tap into different aspects of popularity. So the first thing is somebody's social skills. The second one is if you can measure how selfish they are. You can also measure how interested they are, how others find them interesting. So we can say, for example, on a scale of 1 to 5, can you rate how interested are you in other people? So you can get a measurement there. The proportion of time they spend talking about other people in a conversation. So if you go in a conversation and you talk about the other one, but you can also measure the proportion of time spent talking about themselves. So if all the time you're talking about Thomas is a very good person and all that, so these are the different aspects of what makes somebody popular. So we can measure, so these are the variables. The social skills is a variable, selfishness is a variable, interest is a variable, talk 1 is a variable, talk 2 is a variable, and then our popularity is the factor. Our popularity is the concept that we want to, so this is the underlying factor, underlying concept that we want to measure. Okay, now let's assume, no, I don't have the link of the book here. Okay, so now let's say after you have gone to the field, you've asked, maybe you ask 100 people, and they tell you about talk time, about social skills, about interest, about talk time to selfish and lying, whether somebody's able to lie or not. So now what we see here, this is what we call a correlation matrix. So a correlation matrix is supposed to show a linear relationship between two different variables. And now, for example, here, the correlation between talk 1 and social skill is positive, is 0.772. So that means that a person who talks more about others also tend to have higher social skills. Now, a person who talks more about others also tends to be, people tend to find that person more interested. Then the person with social skills is also, let's first go back here. So how interesting others find them, okay? So here we can see that a person with high social skills tends to be considered, others tend to find that person interesting. So you can see from here that we have three variables that actually are highly correlated among themselves. So this variable seems to contribute to something. They're related. That means they must be measuring a similar aspect. And then let's say they're measuring what we have as factor 1. And then the second one here, now when you look at the others, you can see that talk time 1 and talk time 2, talk 1 and talk 2 are not correlated. So that means if you cannot talk more about other people while at the same time talking about yourself. So that's why they're not correlated. People who talk more about others are not, I mean, they tend to be less selfish, although it's not very high. But now if we come here, we seems to see another thing taking place in this side here. Somebody who talks more about themselves seems to be positively correlated to selfishness. Okay. It's also, if you talk more about yourself, you also tend to be more of a liar. Okay. So you can see this good aspect and these are negative aspects. Okay. So here from this, remember this is a multivariate set. So we have variable 1, variable 2, variable 3, variable 4, variable 5, variable 6. So with multidimensional reduction is we are interested in reducing this variable to say 2 principal components or 2 factors and so on. Okay. So is this matrix clear to everybody? Okay. Everybody seems to be okay with that. Good. George, you saying no? Okay, so let's proceed a bit. Okay, so factor analysis strive to reduce the error matrix down into its underlying dimension by looking at which variable seems to cluster together in a meaningful way. So from here, we seems to see that these variables, these clusters here, cluster together, and they seems to indicate that it seems to indicate aspects of somebody really being very social. And this one here, it seems to look at something like antisocial or something related, not caring about other people or consideration about other people. Okay, so we can see that we have 2 clusters. Okay, so reduction is achieved by looking at which variable correlate highly with a group of other variable, but do not correlate with others outside the group. So we can see from here that these ones here correlate among themselves, and then they don't correlate well with the rest. You see when you look at these values here, they don't correlate with the rest. The correlation with the rest are quite low. And this one also correlate among themselves, but they don't correlate much with the rest. Okay. So in this example, we have 2 clusters, which we can translate, say, 2 factors. So one factor could be general sociability, and then the second factor could be consideration for others. So the question is, if we get one person, how do you score in relation to factor 1? How do you score in relation to factor 2? So based on your score relation to factor 1 and the relation to factor 2, we can tell whether you are social or not social. Okay, we can tell how much you have consideration for others or not. Okay, so based on this, we can also later come and look at plot so this is our factor 1 and that's our factor 2. So you see factor 1 have a high score. You can see this group here will have high scores. The scores are from here. They have high scores on factor 1. Okay, so talk time 1 is highly correlated with sociability. Interest in others is highly correlated with sociability. Social skills is highly related to sociability. But when it comes to the consideration, which is factor 2, you see their scores are all in a small range from, I think they fall between they fall under 2 or 2.5, 0.25. Let me first clean up. Okay, so you can see from here that all these variable here have these very low scores. Okay, but this group here have high scores on that. So we have two groups here. Okay, if you talk 1 is highly correlated with sociability, interest is highly correlated with sociability, and then social skill is also highly correlated with sociability. Now, when we come to consideration for others, then you have selfish, talk to, and liar having high correlation here, but low correlation on the sociability factor. So this is what we have. So the coordinates of the variable along each axis represent the strength of relationship between the variable and each factor. Okay. And if, for example, you get some variable that seems to fall somewhere here, if you're constructing questionnaires and you get variable that seems to fall here, now these variables are not contributing to this and are not contributing to that. So these variables probably are not very useful as far as your construction of the questionnaire is concerned, if you want to measure popularity in your population. Okay. So in the ideal world, a variable should have a large coordinate for one of the axes and a low coordinate for other. So here, for example, talk time has a very high coordination with sociability, but then it has a very low one for consideration. That is what we have. Okay. So we would prefer a variable to relate to only one of the factors. But in reality, this may not necessarily be the case. And in some case, if you had people talking about rotation, so rotation may come in to help so that we have a situation where we have a very clear distinction between a variable and the factor. A variable that have a large coordinate on the same axis are assumed to measure different aspects of a common underlying dimension. So all these ones here are measuring different aspects of sociability. All these ones are measuring different aspects of consideration for others. So the coordinates of a variable along the classification axis is what we call as a factor loading. So if you're going to look at the results of factor analysis, you're going to see what we call factor loading. So factor loading can literally be thought of as a Pearson correlation between a factor and a variable. So the higher the value, the more they are correlated. So mathematically, this is how we would represent a factor. So you have your factor, factor 1, and then factor 1, this is the loading for variable 1. This is the loading for variable 2 up to variable n. So we have this as the loading for the different variable. So for the case of our toy example, sociability, you have B1 and talk time 1, B2 and social skills, B3 and interest, B4 and talk time 2, B5 and selfish, and then B6 and lying or being a liar. So these are what constitute the linear part of the linear. So here we certainly have what we call a linear combination, like we talk about in principal component analysis. So these are linear combinations. So what we can see from here that each factor is a linear combinations of the variables that you have. So each factor is a linear combinations. Now the question is that at some point, this may contribute, like sociability. This one was high, this one was high, this one was high, and then the other ones were low. So this means these values are going to be low, this value is going to be low, and that value is going to be low. Then when they go to considerations, these values will be high, will be high, will be high. So if we are, so the B's are what we call the factor loading that we're talking about. And the factor loading are relating to the correlation between the factor and the variable that you're dealing with. So from here, we can see, if we are to put the value, you can see the loading for talk 1 in sociability is 0.87, 0.96 for social skills, 0.92 for interest. And now look at the rest. You can see 0.0 for talk time 2, 0.1 for selfish, and 0.09 for lying. And these are the ones that we have here. So these are the first 3. And these are the next 3. So that means our factor 1 are mainly in charge. These are the ones of interest in factor 1. When you come to factor 2, you see now the thing change. And then these ones are no longer contributing much to that. Okay? So this is how a factor matrix looks like. These are the betas are our factors. Okay. So we now know, at least we know about the factors, we know about the loadings. So the interpretation of factor analysis is helped greatly by a technique known as rotations. So rotation can either be what we call orthogonal rotation or an oblique rotation. So when we look at this example here, if I try to clean it up, you see this one is a clear-cut difference here. You have this group here and you have that group there. There may be a time when things are a little bit shabby. You can have the thing running all over the place. So if you do rotation, it might make you have a better picture of what is really going on within. So with orthogonal rotation, so each factor will be independent of each other. That means the correlation, the loading is the correlation between the variable and the factor. So here you can see that we have 2 factors. The first factor only deals with the first 3 variables. The second factor deals with the third, the last 3 variable. So in this case, we can actually look at this as some kind of orthogonal rotation, because they create factor analysis factors that are independent of each other. Now you can have what we call oblique rotation. So with oblique rotation, we allow for the factors to be correlated or related to each other somehow. So we are not going to have a situation where you have a clear-cut differences like this, where this is off here and that. You could have a situation where one of these could be in both groups. And it also depends entirely on what your theory tells you. Okay, so the correlation between the variables and the factor will differ from the corresponding regression. So there are different ways of looking at your linear combinations. Somebody has raised their hand up. Are there some question that I need to answer? Yeah, so he said the betas are correlation coefficient. Yes, the betas are correlation coefficient. Rotation is also reduction. No, rotation is not necessarily reduction. Rotation is just you're trying to, it's trying to manipulate the system so that you can get a better view or a better result, or your result should be able to give you a better theoretical representation of some sort. Okay. Yeah, so we looked at the loadings. Okay, the next thing is the scores. So what we want to do is then that each person should then be scored based on the factor, because at the end of the day, we want to know in terms of factor one, how do you perform? In terms of factor two, how do you perform? Can we consider you to be somebody social or somebody highly social? Or can we consider you to be somebody who is not social? So that means since we have this equation here, for sociability, what we simply need to know is that if we have somebody called Dennis, with some information relating to Dennis, so we could substitute. Let's say Dennis on a scale of 1 to 4, on 1 to 5, Dennis has a score of, let me first clean it up a little bit. So we can have a situation where this person talk 1 as a score of 4, and then on social skill as a score of 9, on interest as a score of 8, on talk 2 as a score of 6, and then on selfish as a score of 8, and then on lying as a score of 6. Now you can see the scores are not that different, but the coefficients are the ones. So in terms of sociability, this person scores 19.22. And then in terms of consideration, this person scored, say, 15.21. So probably what we're saying is, I think the scores are, maybe this person seems to be neutral a bit. 19.22 versus 15.24. So it's more on the sociability side, but it also scores somehow high on the consideration. Now, this is what we call the weighted average method, which you simply plug in the values. There is also what we call the regression-based method. I'm not going to go deep into it, but then it also calculates for you. So when you look at a regression-based method, something strange seems to be happening here. Of course, the values are much closer together, but also we can see that there's a switch. In terms of sociability, the person has a lower score compared to consideration. But in general, this person seems to be somewhere in the middle. There are a majority of people who don't belong to either side. There are people who would outright consider to be score very high on consideration and very low on sociability, and so on and so forth. Now, the naming of the factors are actually very challenging. The naming of the factors will depend entirely on you as a specialist and how you understand your field. But what we are trying to give you here is we're just trying to show you what is available, and we give you the tool. It is you to decide what you want to use with the tool. When you fail to use the tool, don't blame the manufacturer, because the manufacturer gave you the tool and with the instruction. So we are giving you the clear instruction on how you can use the tool. So how do we use factor analysis, factor scores? So any further analysis can be done on the score instead of somebody's asking, do all variables need to be in the score, the same range? No, the variable don't need to be in the same range. Okay, so one thing is then that we can actually use the score to compare a female more social compared to the male, or using the sociability scale. So you already have a variable that you can now use to run, but you can also use this to do regression analysis. So now if I have all the measurement on sociability. I have measurements on considerations. I have measurement on another, say, third variable. I should be able to put them together, and then I run my regression analysis. Okay, so now choosing method for running factor analysis. So there are several ways of doing factor analysis or unearthing factor in your data. So your choice will depend on what you want to do with analysis. If you want to do just an exploratory, a descriptive, you can do exploratory factor analysis. In most cases, people do more exploratory factor analysis. Or you may be interested in confirming or generalizing from sample to population. Then in that case, you can do your confirmatory. So the first thing is you need to choose, are you going for exploratory or you're going for confirmatory? So you may need first, so the factor analysis was first built for exploratory analysis, and then that will use to generate the hypothesis. You can also use what we call the principal component-based method. So the principal axes are used as your factoring. In that case, the conclusion can be restricted to the sample. You can also use another method, which is the maximum likelihood method, or there's also what we call the Kaiser alpha factoring method. Now, for these two methods, the conclusion can be applied to the population, but restricted to the variables used. The challenges with choosing multivariate analysis always, if your level of understanding what each factor what each variable, each analysis does, you're likely to choose the wrong method. First of all, you may choose the right method and still you also do, you can choose the wrong technique, or you can pick the right technique, but still within the technique, you can still mess up. So to me, since this is the first lecture or the first training we have had on multivariate analysis, I would suggest, first of all, if it is your first time, first of all, pick the general concept. After picking the general concept, you need to get a bit more time, go down and try to look at the individual technique that you want to use yourself. So if you want to use multivariate, you want to use principal component analysis, then I would suggest then that you go to the principal component analysis and try to understand more. There are several examples, there are several tutorials that are available online. You can run them, and then you should be able to at least perfect your skills before you can go and do the analysis. A few more slides to go. When we are doing factor analysis, there is a term called communality, which is very, very common. Now, when we look at this correlation, variance, covariance, or correlation matrix, we can see that we have values of one across the diagonal. And these values of one across the diagonal are actually, these are actually the variances divided by the variances themselves. Okay. So here, the total variance for each variable. So what we are saying here is that if you go and look at the data you've collected on talk time 1, of course, if you talk time 1, you're going to get, there's going to be variation. Okay, there's going to be variance. So since there's going to be variation, people will give you different responses on a scale of say 1 to 5. So part of this variation here is shared with remember this DC3, we said that there seems to be they're dealing with one factor. So that means there's some variation that they share among them. So there's variation that is shared with the social skill. There's variation that is shared with interest. So this is what we call a common variance. So variance shared with other variables. And then there is the unique variance. So unique variance is going to be variance that is specific to that particular variable. Let's say variance that's specific to talk one. And part of that unique variance, in the strictest term, this unique variance should be the variance that is only attributable to only one measurement. I mean, in other words, there is that component of the random noise which is also included in. So this unique variance here has something, it has what is unique to the value, but it also has some kind of noise that is associated with it. But the key thing here is that when you go to look at the FA factor analysis output, there is going to be what we call the common variance, and then there's going to be what we call the unique variance. Now, you want the common variance to be high because you want them to be related to a certain factor. Now, if the commonality is equal to 1, that means there's no specific variance. If the commonality is equal to 0, that means there's no common variance. So all the variance will be specific to that particular variable. So in factor analysis, the interest is in the common variance. We want the common variance to be as high as possible. Okay, so we can have some questions, and then I saw there are some people with their hands up. Is it raised accidentally or? Okay. It's a relationship between principal component and FA in terms of variable within both approaches. For experimental research, can I just do principal analysis without trying to create factors? Now, the first one, I'm actually trying to. Okay, so principal component is mainly. It doesn't really stress that much the importance, the issue of the factor. But if once you bring in the issue of the factor in the principal component, then you're already doing factorial. But principal component analysis is a lot used more as data reduction, and principal component does not. You see, principal component, we are looking at the amount of variance that is explained by the first principal component. While in the factorial, we are looking at the amount of the common variance that is explained. So that's one kind of unique difference, that the principal component analysis look at the total variance that is explained by the principal component, while in factor analysis, we are interested in that common variance that has been explained in that. So for the question, for experimental research, can I just do principal analysis without trying to create factors? I find principal component analysis as one of the method that is highly abused, especially by plant breeders for some reasons. I find it a bit difficult to recommend it, apart from maybe it looking fancy, when you have really very few data sets, you have very few observations that you're trying to get. To me, the question is, if I want to use principal component analysis, I need to ask myself, why do I want to use principal component analysis? Do I want to look at the relationship between the different variables? Because I have seen sometimes somebody comes up with the principal component analysis. There is nice principal component analysis where you also put in you also put in the variables together with what you're trying to classify. That's also fine. Yeah, but you have to be a little bit more careful. Okay. Can PCA handle open-ended questions? No, principal component doesn't handle open-ended question. Principal component are based on numerical values that you have. So they can handle Likert scale, but it cannot handle open-ended questions. In case variables are weakly correlated, now if the variables are weakly correlated, there is actually no reason as to why you should do principal component analysis or factor analysis. Because at the end of the day, the assumption here is that if the variables are related, then you can get an underlying factor. Now, if they are not related, there will be no underlying factors. And the number of principal components that you will get to explain the amount of variability in your data is going to be very high. And at the end of the day, it doesn't make sense. What will be the option for plan breeding data set if No. There are very many things you can do with your data. I'm not saying you should not do principal component analysis. I'm saying there are many other tools that you can use. So in my opinion first have your principal component analysis result and then try to interpret it. Now, in one way, of course, the easiest way if you can interpret and you find it falls nicely within it falls nicely within your within your theory and what, that's fine. Go ahead with it. What's the main difference between PCA and principal coordinate analysis? I think PCA deals directly with the raw data. PCA or principal coordinate analysis, you first convert the raw data into distant measures and then you do the decomposition. That's the main difference. But otherwise, the interpretations are very similar. Is the rule of thumb that if you want to do factor analysis, you perform PC first? Not necessarily, but what we're going to see in ARA is that you can have the factors are already done. You don't need to worry that much about that. Supposing you have a lot of variable with one factor, can't you do a PCA then do exploratory? The PCA and exploratory are done for different, the PCA and factor analysis are done for slightly different ideas. So, okay, we are going to run some analysis. Let's have a small break. Let's have 10 minutes break and then we come. So as we're going to have the break, my colleague has shared for you a folder with the material for today. So I want you to download the folder, put it on your desktop or somewhere because we are going to use it for the analysis. Okay, so we're going to have 10 minutes of break. We come back at 15:36. This folder for day 3. I mean, doing PCA and doing PCA before factor is not going to change the relationship that you have. Your factor analysis and your principal component analysis result is going to be based entirely on this table here. So the variance covariance matrix or the correlation matrix is the one that is going to determine whether you're going to get different, you're going to get many factors or not. Please download the folders. We cannot send it through email, please. There are so many people. Day 3 material. Please download day 3 material. The link should have been provided a few times more already. Yeah, you first unzip. Once you download, please unzip. Okay, let me take some water. Thank you. Hello, welcome back. Yeah, we have a very, very simple uh, practical to run. So the first thing I want to know is how many people have the file? Okay, good. We seems to have a number of people with the file. Have you zipped the file? Okay. So please, those who are, I'm going to give you another 5 minutes to ensure that everybody pick the material. They can be, okay, let me hope they'll send the link. Somebody will resend the link again. And somebody who is having challenges want to be sent on email, I don't know. Can one good Samaritan send an email for Frederick? The link is going to be pasted back. It's going to be put back here. Okay. I think Ellen has put the link. Can you please download and share with your colleagues? There are lots of online materials that you can actually try to run. So you can go on YouTube. Hmm? We have a CSV file which can be opened in Excel, so that's okay. Yeah. Okay, so let me try to look at the. Let me try to get the folder so that we see the content of the folder. Okay, so in the folder, there are three files. There is a fact analysis, a PDF file. There's factanalysis.ara, and then there is a testscore.csv. So these are the different files that I want you to have. Now, I want you to open the factor analysis.r. You can right click and open with R Studio. Open with R Studio. I want you to, so please make sure you're first seeing what the content. How many people are seeing have the files? Can I see people typing yes, those who have the 3 files in the folder? Okay, I think we have a number of them. I'm not seeing any no. Okay. Okay, so the next thing that I want us to do is I want us to open the second, you see the second file, the one that ends with .r. I want you to right click on it and then say open with RStudio. Once it's open with RStudio, you should be able to see, let me now stop sharing this. Okay, so what I want you to do is I want you to okay. So what we first need to do is we need to install the two packages. There is a psych. So you need to run line 1 and line 2. That is a must. So if I run my line 1, it's already telling me updating the loaders, but so I say cancel. So I've already installed. So I want you to install the two files, two folders, not folders, sorry, two packages. And once you've installed the two packages, I want you to run our line number 3 and number 4. So what we know is that for you to use ARA, you need the package, and the package can be installed using install.packages. The first two lines are used for installing the packages. And then once you've installed the packages, you still need to call the packages using the library. So you can run line number 3 and run line number 4. Okay. So is that done? Have we run number 3 and 4? Can I see in the chat? Okay. I seems to see some. Anybody an error? Anybody we've seen an error to show us the error? We said warning package psych was built under that. Wait a bit. The Tabita, you don't have the I. You're saying install, not install. So you need to bring the I there. That's why you're getting the error. Tabita, can you do that? Just run the line the way, just put a cursor on the line and run it. And let me see if you've done right. You can type yes. Tabita, can you type yes? The rest seems to be okay. Okay. Now the next thing that I want us to do is, I want you to go to the, do you see on top where there is RStudio file? I want you to go and look for where it's type session. I want us to look for, to make the folder that has our data set, we want to make it a working directory. So you go to session, go to set working directory, and then you choose a directory. Tabitha, what issue do you have? Can you allow Tabitha to share a screen? I can stop sharing the screen. We want to see. I'm going to stop sharing the screen. Can we make Tabitha to become a host? Or let me just, okay, let me say not panelists. Allow Tabitha to share so that we see where the error is coming from. Somebody said the error studio is not opening. Dr. Nyararo, can you make, can you promote Tabitha?
I promote who?
Tabitha.
Okay. Tabitha Hukamau na siku.
Samuel, I think you should be okay. Tabitha, can you share your screen?
She's rejoining.
Okay.
I don't know which Tabitha you meant.
There is, I don't know whether there are more than one Tabitha, but I saw one Tabitha.
There's one Kamau is declined. Yeah, two. There's Tabitha Naisiko is now she's now a panelist, so she can actually share a screen. Tabitha Naisiko. Naisiko, kindly share your screen. Unmute yourself and speak. Yeah, please go ahead.
I think I've seen where the problem is. It tells me that I'm not installed.
Okay, Dr. Odong, you want us to promote another person?
Okay, I'm failing how to
share the screen. Look for the green icon.
Green, okay.
Have you seen it?
Yeah.
Yes, click on it and then choose the window which you want to share. Good. Go ahead.
So it tells me that packages are not installed.
Tabitha, can you click on install? Do you have that one, that warning on top there? Can you click on install? Yeah, that one. Click on install there. Let's wait and see. First wait. Okay. Can you run library, run line 3 and we see? Okay. Run line 4. Okay, you're fine.
Okay. Thank you.
If you see any note on top indicating that you need to install, you can just click install.
Okay.
Okay, you can stop sharing now. Any other person having a problem who wants to share the screen? Okay, so I can assume You cannot install Edward, or Kudumu. Can you promote Kudumu, Edward Kudumu? But you have not written it correct. Your name is not written. You decided not to write it correctly.
Edward.
There is Kudumo.
Oh, okay. He's joining. He has declined.
He has declined.
Mm.
You cannot see install. But he said he has not declined.
He has declined. I see whenever I try to promote someone, I see a person who has declined.
Hey.
Yeah.
Okay.
It is even now it is saying he declined to be promoted.
Okay, let's just try to run.
Okay.
Run with the people who have, and then we can see later. There is Samuel Samuel Malogai. Can you promote that one? Maybe then we run.
Yes, I
Malo
joining.
I'm reading Latin.
I have requested him to read
By Kang.
Yes.
Kang.
Yes. I do not know why. Yeah, he's here. He's sharing his
Okay.
screen.
Line 4 is saying that after I run line 4, it's saying attaching package. GPU rotation. The following objects are masked from package.
No, but that's okay. That's not a problem.
Okay.
That's fine. You're okay.
Thank you.
Yeah. Okay. So let's find that you can stop sharing and then we proceed. Okay. So I want you to set a working directory. How many people can set the working directory? So you just go on top. There is you see mine the app session. Set working directory. Choose the directory. Just see what I have there. And then when you choose a directory, look for the file, the folder that you just downloaded. That is where I want us to work on. You see, at the end of the day, you should be able to see what I have done on my console here. Once this is done, then the rest are all going to be easy to run. Okay. So I assume that all of you have set a working directory. So the next thing that I want us to do is try to run your line number 10. Line number 10, which is we are trying to read. This is the command, read.csv. We are reading test score .csv. This is our file that we are trying to read. So let's run line number 10. And then we can check using this command add. We can run this. So you should be able to see that here we have the results for 8 tests. Test 1, test 2, test 3, 4, 5, 6, 7, 8. So these 8 tests were given to a group of students, and each of them got some scores. Now we want to see, the first thing that we want to do is we want to see whether there is correlation between the different tests. If there is correlation between the different tests, that means we can go ahead and run our factor analysis. If there's no correlation, that means there is no need for running factor analysis. So we can do core-test.bartlett for using the data set itself. So here, if we run line number 12, okay, it should be able to show you some warning here. Error was not square, finding error for the data. So here you can see it gives you a chi-square. That is 678.8. It gives you a p-value, which is 5 times 10, 5.17 times 10 to power negative 125. Is this a small or a big probability? And it gives you 18 degrees of freedom. So so what we are trying to test here is we are testing whether there is a correlation between the different variables. So we are testing whether we have an identity matrix or not. Now, the null hypothesis indicates, the null hypothesis is that we have an identity matrix. With identity matrix, that means we have ones across the diagonal and 0 elsewhere. Zero correlation means there are no relationship between the different variables. So if we reject the null hypothesis, then we should be able to go ahead and do our factor analysis. So let me see from the chart. How many people have run? Okay. How is the directory chosen? So for the directory, you go to session. If your line number 9 refuse, first let's go to session. I hope you're seeing my screen well. Session, set working directory, and choose a directory. That means you need to know where where your folder is. Anybody wants to share so that we can get your directory? You can help the rest to see. Anybody want to share? Just type I want to share. If you're failing to get directory, yes, there's Onuka Okori. Can you promote Onuka Okorie to share? So that we can try to solve the problem. Yeah, the test scores are the variables in this case. Is somebody being promoted to share? Let me stop sharing.
Can you let me know the name you want me to
There's Okorie, Onoka Okorie.
Okay.
Okorie.
It's
like the
Okori.
name of, almost like the name of your boss, only that E is not there.
Okori, hey, he's joining. Okori is joining. Yes, Okori is there.
Okay. Is my friend. Okay, so we want to see where you are. I'll wait a bit. Choose a directory. You wait a bit. What's happening? We are not seeing the directory thing working. Can you do it again? Uh-huh. Where are you? Can you first install the, I want to see whether your system works or not. Can you install the, just click the install. Oh. Can you try again and we see? No, don't install again. You're okay. I want to see try to. I don't why I don't know why the system is not working. Mm. No, you need to first set the working directory. So if you don't set the working directory, then you will not be able to get there. Okay, fine. These things are quite. Let's first run. With the I think there's just something that seems not to add up. Yes, not installed. Where? Okay. Let me just proceed and we run now. We will look at the rest will follow first. Let's first follow on the screen. Okay. So the first thing here is we need to test whether we are dealing with an identity matrix. An identity matrix means the diagonals have ones and then the off diagonals have zeros. And that means in that case that there's no correlation between the different variables. And once there's no correlation between the different variables, there will be no need of running factor analysis or principal component analysis. Okay. So now let's go and run our line number 13. In line number 13, what we are trying to do is we are trying to run correlation between the different variables that we have, the 8 variables that we have. So let's run line number 13. And then we can print what we have generated. Remember, we created an object called core subset. Now, what we need to do is we want to print, but we want to round off to 2 decimal places. So run line number 14. Okay. So if you run line number 14, you can see that there is a correlation between test 1. what do we have a high correlation between test 1 and which test? Can I see on the chart? Test 1 and which test? Test 1 and 4. And then test 1 and 6. So you can see here we have 0.74 for test 2, 0.79 for test 4, and 0.79 for test 6. So that means test 2, the test 1, test 2, test 4, and test number 6 seems to be related. They seems to be measuring one thing. Now, test 3, very low correlation with the test 1, test 5, and then test 7 and 8. Now, when we go to 2, we should be able to see the same thing. With the 1, with the 4, and with 6. Now, when we go to test 3 has high correlation with test 5. It has high correlation with test 7 and high correlation with test number 8. Now, we have across the diagonal, we have 1, 1, 1. So 1, 1, 1, that this is the variance, the covariance with itself. Okay, so from here, we seems to see that there seems to be two groups. There is 1, 3, 4, and 6, and then there is 3, 7, and 8. Okay. Now what we are going to do first is we are going to run our factor analysis using this function here, which is factanal, and it's going to give us some information here. So let's run line 18. Of course, if you run line 18, you don't expect to see anything because we have created an object. So when you've created an object, so in this, what we're doing is that we are running this function here. The data set is our score. Remember, this is what we got from here. And then the number of factors, we say we want 1 factor. We are just specifying 1 factor. And then later we're going to look at 2 factors, 3 factors, and so on and so forth. So we can look at 919. We have created something which we call EA-1. So we want to see what is this. Now it tells you this is factor anal because it's created from that function. We can also look at the loadings. Remember, we talked about the loading. The loadings are the betas that we are talking about. So let's create an object called the loadings. Okay. And then it's the same command twice. So we can run line number 23 here. Okay, so we're just picking the first value, which is 0.001131. Now let's look at what is the structure of this loading. It has something, it has test 1, it has factor. So, but let's run our line 25 first, then we see what is there in line 25. Okay, so with the line 20, remember here we have our factor. This is for we have only 1 factor. Now, if you remember, this is for test 1. That means this is the beta for B for test 1. This is B for test 2. This is B for test 3, for test 4, for test 5, for test 6, for test 6, for test 7, and test 8. So you can see now that which variables are having high correlation with factor 1. Can you type in the chat which one have high correlation for factor 1? Remember, this is the first factor. Can I see in the chat which one has high correlation with factor 1? Okay, say 3. Yes, 3 has a high correlation. 5, yes, 5 also has a high correlation. And then 7 and 8. Okay, and those ones, the one that we saw initially, the one that are here. Remember, 3 had a high correlation with 5, had a high correlation with 7, had a high correlation with so those are the ones that are picked as our factor number 1. The other thing that we can do is we can square the loadings. We can square the loading, square each of the loading, and then you sum them up. So that's what we call the sums of the sums of squares. So let's run our line 26. We're going to make it so you can see the total loading sums of. So it's just simply this squared plus that squared plus that squared plus that squared. Now, if we sum this one all and we multiply by the total number of columns. Now, remember the total number of columns are the total number of tests that we have. We have 8 different tests. So here we are going to look at the proportions of variance that is accounted for the whole data set by the first principal, the first factor. So what we're going to do here is we run here. So you can see that the first factor account for about 40% of the total variability that we are observing, the total proportion of variance that we have there. The sums of the loading is what I'm trying to explain. The sums of the loading is trying to explain the proportion of the variance that is explained by the factor. So the first factor explains about 40% of the variance that we observe, but we are going to get a much better results later. Okay, so now what we did here, we ran this line 18, we specify 1 factor. Now let's go and specify 2 factors. We are going to run the same command, but this time we're saying n is equal to 2. So let's run line number 29, and we look at the output from line 29. Okay. Okay. Now the first thing that it gives us here, it gives us, we say, uniqueness. Now remember we talked about that the 2 components of the variance. There's the variance that it shares with the other variables, and then there's variance that it for itself alone. So you can see from here that 0.23 is for test 1 alone, 0.22 for test 2 alone, 0.17 for test 3 alone, and so on and so forth. Now, we have our factors down here. Okay, so here, these are our loading. So remember here, we specify that we wanted 2 factors, factor 1 and factor 2. Now, when you come to test 1, you see test 1 here, it doesn't have a loading on factor 1. What happens is because now R will decide only to print up to a certain amount. So you can see from here that, so we assume where these are zeros. So factor 1, test 1 has a no loading on factor 1. It has a 0. It has a 0 on 2, also has a 0. 4 also has a 0. And then 6 as a 0. So this factor 1 is the factor that is associated with test number 2, test number 3, test number 5, test number 7, and test number 8. And then our factor 2 is associated with test number 1, test number 2, test number 4, and test number 6. So remember, this is what we saw in the correlation that we have before. Now let's go and look at down further at the sums of squares for the loading. Initially, our calculation on line number 27 gave us this value already. And then for factor 2, we have, this is the value. So you can see from here that factor 1 gave us 3.217. Factor 2 gave us 3.09. Now, in terms of the proportion of variance that factor 1's accounted for is about 40%. That is what we calculated in line 27. And then factor 2 accounted for 38%. And remember, the same principle like what we had in principal component analysis. The first factor is the one that that counts for the highest, followed by the second, and then the third and the fourth. So we can run 3, 4, 5, up to 8. And then the cumulative. So the first one is 40%. The second one, so cumulative. So the first two factors account for 0.78% of the variance that we are dealing with. And then here we have a test. So what we have a test here, and this is the test hypothesis that 2 factors are sufficient. So this is what we're saying. Test that 2 factors are sufficient. Now it uses a chi-square test. So here it gives us a chi-square statistics of 15.18 on 13 degrees of freedom. And then it gives us a value of 0.296. So I want to ask you, based on the p-value, can we conclude that 2 factors are sufficient? Somebody said no. Somebody said yes. Okay. Okay. Now the first thing is, let's look at what is our null hypothesis? The null hypothesis is that 2 factors are sufficient. Okay. Now, are we rejecting the null hypothesis, or we are failing to reject the null hypothesis? Are we rejecting the null hypothesis? We are not rejecting the null hypothesis. So in this case, we fail to reject the null hypothesis and therefore conclude that actually 2 factors are sufficient. So since we failed to reject the null hypothesis, we conclude that 2 factors are sufficient. Now let's look at we ran the first one with principal component 1. Okay, with principal component 1, our chi-square was 327 on 20 degrees of freedom. It gave us a p-value of 1.92 times 10 to the power negative 57. Now, this is a much, much smaller probability, smaller than 0.05. So we reject the null hypothesis that 1 factor is sufficient. So that's why we went and ran 2 factors. Now, let's run 3 factors and see. Okay, so when we run 3 factors now, and you're going to see this also on principal component, you're going to see the same thing. Okay, now you see the uniqueness are also going, the values are changing. Okay, so the factor 1, we still have our test 3, our test 5, our test 7, and our test 8. And then factor 2, we still have our test 2, test 1, test 2, test 4, and test 6. And then we have a third factor that seems to say something about test number 4 and test number 5. But remember here, we already indicated that actually 2 were enough. But we still ran out of curiosity. Now let's look at the loadings here. Okay, so the sums of squares are reducing. So you can see now that in terms of the proportion of variance that is accounted for, now this one actually accounts for very, very small percentage. And so we can see moving from the second factor to the third, we gain about, we go from 79 approximate from 80 to 83. So here, we already said there is actually no need of going for 3 factors, but we just ran the 3 factors because we wanted to see exactly what is going on there. Let's run 4 and see what comes. Okay, so we still have our factors. The first 2 factors are intact. We have something happening in factor 3, and we have something happening in factor 4. Now, in most cases, if like when we run principal component analysis, the later principal component may actually be giving some kind of finer relationship that maybe could, for example, you could be looking at things like identifying some outlier or some individuals that are very, very unique. So when you're going to do principal component analysis and you plot the first two PCs, we assume that those ones always capture as much of the information as possible. Now, any additional information now will move on and become less and less. So here, so you can see that the first 2 factors will give us about 80%. The first 3 will give us 82%. The first 4 will give us 84%. But you can see from 2 to 4, we have gained very little, about 4%. So this is where the issue of parsimony comes in, that do we want to go in for many factors? And yet they are not giving us adequate explanation. But the good news is, at least from here, when we tested the 2, it already told us that the 2 are sufficient. There's no need for going for a 3rd factor or a 4th factor. Now, once we agree that the 2 are sufficient, the next thing would then be, how do we interpret the 2 principal components, or the 2 factors in this case? Now, so you need to start looking at that, okay, maybe the first 2, let's say these students they came when they're very serious. So they passed the first two tests, and then they somehow relax again. And things did not go well in the 3rd test. Then they picked up again, then they relax, then they pick up again. But here you could have a situation where for factor 1, these are people who came and first started sleeping, and then they woke up at some point. But now it has to be you to look at the factors and interpret it in light with what you know as a specialist in your particular field. Somebody said they could be retakers, or they could be, yeah, so this is the one. They could be retakers. They were not attending. Then all of a sudden, somebody comes and then attends and then disappears and then comes and then, yeah. So as the semester comes to an end, they can move in and have this. But this data was just generated. The other thing is that you can also use a covariance matrix to run. You can also use covariance matrix to actually run the factor analysis. So instead of using the original data, remember we use the score. So you can use cov score. You can create a covariance structure, and then you can round it off and you see what is going on. So here you have the different variance. This is the variance covariance matrix. You still pick up that there is the test 1 and test 2, test 1 and test 4, test 1 and test 6. But here also, we don't have the 1 anymore. This one here now is we have 0.9. 0.9 is now the variance. So this is the variance for test 1, the variance for test 2, the variance for test 3, and so on and so forth. Now we can run the same function, but now we are using a covariance. So you need to check how it is defined. This one say covariance matrix equals to covmat, 2 factors. We can run this, and we should still get the same result like what we got before. So what we're saying here is that you can actually have a covariance matrix and not the actual data, and you can see use the covariance matrix to move on and have that, okay? Now remember we talked about the scores, and we look at the factor scores, and we said there are methods. You can use weighted method or you can use a regression method. So let's say, for example, if we use a regression method, so these are the scores on factor 1 and factor 2 of the first 6 individuals that you have in your data set. So I could have for all of this. Wait a bit, sorry, I need to, I just need to get to extract only the scores from there. Okay, so you can see differences. So you can see this person here is high on, oh, sorry. Drag my, okay. And now the other thing that we talked about is we talked about rotation. And we said the rotation is mainly brought about to be able to help us to have a better visualization or a better understanding of what is going on. Yes, somebody said, I think because the p-value already showed us that much of the variation is already explained by the 2 factors. So additional factors are less value true. Okay, so we can run a factor analysis, but this time we are specifying that we want a varimax rotation. So this is one of the rotations, and then the scores we said calculated using regression method. Okay, so we can run that, and then we can extract the scores, the correlation between the 2 factors. Remember, so you can see here, the correlation between the 2 factors is very low. So the correlation between the 2 factors being very low means we have a situation where if a variable has a high loading on factor 1, then it will have no loading or very low loading on factor 2. So we have a situation where this is similar to what called an orthogonal rotation. We can also do another rotation, which is called Promax rotation. So you can just change it from here. I'm not going to go into detail to explain for you all these types of rotation, but I'm sure when you go and read, you should be able to come up with an easier way. So when you look at this, the correlations, you see the correlations, this is negative. Here we have actually the similar value for the correlation. These ones are slightly higher compared to this. 0.001, this is 0.01. So you can see now that with varimax, with Promax, we seem to have some slight correlation between the two factors. So we can run with another. So there is a FA. This FA comes from a psych function. It also runs for you a factor analysis, but then it gives you different output, different kind of output. So let's run this and see what we can get out of it. We can extract the loadings out of that. Okay, let's see. So we still have, okay, so you can see M1, MR1, you have this. So factor 1 is still test 3, test 5, test 7, and test 8. And then factor 2, we have test 1, test 2, test 4, and test 6. And then here we still have our cumulative variance. You can also extract uniqueness. In the case of the first one, it gives you uniqueness. This one, you can extract it. And this value should be similar to what we saw before. You can also extract the commonalities. So the commonalities are the amount, the variance that it shares with the rest. Now, in this case, test 1 will share this 77.8, but it will share it with the test 2, test 4, and test 6. And then test 2, test 3 will share it with the test 3 with, so these are the commonalities. Remember, commonalities, we say these are factors, these are variances that are shared with the other variables. So if you add the uniqueness plus the commonalities, you should be able to get 1. Okay, because that's the total variance that you have, assuming the random part get in 2. Okay. So 2 different methods for calculating, they give you slightly different results. Then we have a third one. We can use the function principle. So in this case, you specify your score. This is the data set, how many factors you want, and then rotation. Do you want rotation? Here we said no, none. You can have the different type of rotation like we saw before. So we can also run this and we get similar results. So if we run this, okay, so let's look up and see the kind of results that we have. So here we are looking at, we want to have 8 factors. Remember, we have 8 tests. So 8 factors mean the number of factors the same as the number of variables. So apparently you're almost not doing anything. Okay, so let me check, go up here. Of course, here is typically gives you principal component. Okay, so you can see the first principal component, the first PC, and then you can also see that the first PC is scoring highly on 3, on 5, on 7, and on 8. The second PC is scoring highly on 1, 2, 4, and then on 6. Now the third one, you see the third one seems to be nothing really in particular, the fourth one, and so on and so forth. Now, it also gives you the H square. H square means like the variance that you have. Now, then, so here you have the values of 1, 1, 1, 1, 1, and then it gives you this is uniqueness, because now the commonality is this is representing these are 1, 1, 1. So these ones are 0, 0, 0. They're more or less like 0, 0, 0. And then let me go down a bit. And then it also tells you the loadings for the different PCs, and these loadings are converted into the proportion of variance accounted for. So you can see the first 2 accounts for 84%, then 88 and 90 and so on. And then the proportion explained in each case. And then the cumulative proportion explained. We have this. And then here we're saying this is another test. We are testing the hypothesis that 8 components are sufficient. Of course, here, the probability is not there because we are using the entire data set. We are using all the principal. Now, if we change from 8 to 2, remember we're saying n equals 8 and we have 8 different tests. So apparently we are not doing anything because we are running the entire value there. So let's run our line number 71. Okay, and we check what is going on here. So here you see we have two pieces, principal component 1, principal component 2, and then we have our h square, which is the commonality, and then here we have the uniqueness. So this plus that, and this is the amount of the common variance that we have for each variable. Then we have our loadings. This is similar to what we saw before. We have the proportion of variance, the explained, and so on and so forth. So you can see from here that actually the first two principles, explain more or less everything that we have there. And then, of course, we have a nice test here. You see now we have the probabilities here. Initially, we didn't have the probability because we did not have any degrees of freedom. We had 8 variables. We put all of them into our principal component analysis, and therefore we cannot actually do anything out of it. So we can also bring the correlations between the different. Okay, so you can have the correlation between the different tests. Now here you have 1 and 2, 1 and 4, 1 and 6. Remember, these are the ones. And then, of course, here you have your, this is similar to what we had up here. The diagonal one is similar to these ones here, the H, 0.83 and 0.82. You can see here, 0.8, 0.82. So these are the commonalities that you have here. Okay, and these are the correlations that we have. So this correlation is the correlation between the different variables that you have. So there are different ways. You see this correlation here is based on the model, but you can also have correlation that is based on the actual value. Now, the difference between the correlation based on the model and based on the actual value. So let's see, for example, here, remember here is based on our model with 2 factors. Here we can have correlation based on model with 1 factor. You see, with 1 factor, the correlation is lower, but the pattern is still the same. Now, this is the correlation that we started with, the one that is from the entire data set. Okay, so you can see 0.7. And then, of course, the diagonal now is 1, 1, 1, because that is the variance that you have there. So but we can also, this is just more playing around with. So you can actually look at the residual. If you compare this to this, you can see how different is the correlation based on the raw data and the correlation based on model with the 2 factors. So if we run line number 77, okay, so you can see this This is the variance. Now, this variance here is more related to the unique variance for each of the observation. And these are the correlations. So you can see the correlations are a lot. So the difference, this is the difference between, so a bigger part of the correlation was, there's a big, so it's not really big, is it? Because what we want is that here we have a good model that explains 80% of the observation. So the difference between the raw data and a good model should be smaller. Now, if we compare a difference between a raw data, correlation based on a raw data and correlation raw based on one variable, we expect that this relationship should be worse than the previous one. So these values here are smaller. We expect line 78 to produce for us slightly bigger values than what we have before. And if you look here, you actually see, no. 2.6, let me check the other one. No, I think I mixed up the explanation. Let me see what. I think I mixed up the explanation. You like to see MSD2? No, we cannot start something new now. We're just trying to wind up what we have. So if you use the PCR, you can also no, the plot will come later in the next one. The plot will come later. So we can also do rotation. So here we can do varimax rotation. We have 2 factors, we have 4 factors, we have 2 factors. So we can run this, run that. And then we can now try to look at this, but we want to only show loadings that are greater than 0.3. So let me first print this and we have a look at. Okay. Okay, so here, of course, you can see that you have test 3, test 5, test 7, test 8. These are the ones, these are one group. And then the second group, we have this. And then the third group, we have only test 4. The fourth group, we have only test 1. And then this one gives you the commonalities. And then this gives you the unique variance. And then this ones give you the common variance that is shared by the actual value that is shared. Now, if that was for model with the number of 4 factors, we can do it with model with the 2 factors. Okay, so somebody's saying rotation. So rotation is, when we're talking about, before we started doing the practical, we're talking about rotation is one way of how to improve on the interpretability of our, our factors. So you can have what we call orthogonal rotation, which assume independent information is given by its factor, where zero correlation between the different factors, or you can have oblique rotation, in which you can have different degrees of relationship between the different factors. And this is supposed to be based on the kind of theory that you have. Now let's have, so this have an oblique kind of relationship, oblique rotation, which is kind of oblique rotation one of the oblique rotation is what we call oblimint. And this is supposed to, we want to see whether there's going to be improvement in these blank spaces here. But that depends entirely on whether, what kind of relationship we are dealing with. So we can still try. And then I wanted to run in a way that I leave anything else that is below 0.01. Okay, so you can see here. Wait a minute, what do I do? Okay, so here we can see we have 0.9, 0.92, 0 point that. But now we also have these small ones that were there because of what we did here. If we change this to 0.5, we'll see completely a different story. You see, if we change to 0.5, then this one completely remain blank. So you can actually play around with this to show if there are any sharing between the different factors. So you can see here that our factor 1 is purely for those with test 3, test 5, test 7, and test 8. And then our second factor is for those ones with 6, 1, 2, and 0. I think that is more or less. Okay. Okay, so I think that is where the practical for today will end. We have a few minutes to try to answer questions. Categorical analysis is challenging then, but we have grasped it fairly well. PCA, so PCA can then be used to develop theories. Yes, PCA can be used to develop theories, can be used to develop hypotheses. So yeah, we have 10 minutes to wind up.
There's Dr. Dong, there are some questions also in the Q&A, maybe if you could also.
Okay, the questions in Q&A. Okay, let me try to stop sharing and see whether I can answer some questions. What is multicollinearity? Multicollinearity is when we are doing multiple linear regression, sometimes variables, there are variables that are highly correlated. When these variables are highly correlated and you put them into a regression, into a multiple regression, they are literally giving similar pieces of information. And that is what we call multicollinearity. And with that multicollinearity, what happens is that the regression coefficient that you estimate will tend to be very noisy in that they have very high standard error. So that's the what is about multicollinearity. PCA is not the same as regression. You can use the result of PCA into regression analysis. Instead of using your ordinary variable to do the regression, you can have the scores from PCA to run as a variable in regression analysis. Can PCA handle open-ended questions? PCA ensures that with PCA, you need quantitative data. Open-ended question, unless you can relate it to quantitative data, it cannot handle. It can handle Likert scale, because Likert scale will generate for us or maybe values 1 to 5, 1 to 9. Please, in case variables are weakly correlated, could it weakly correlated, could you still be, if the variables are weakly correlated, certainly you're not going to do data reduction because there's nothing to reduce, because each one is supplying independent information. So there is nothing much that you can handle from that. How is the concept of PCA looking for in relation to PCA? Yes, the biplots can be useful. The biplots, both the what we have as the AMI biplot or GG biplot, also P-axon. I mean, they work on the basis of principal component analysis. And in that case, therefore, yeah, they can be useful in understanding genotype by environment interaction. So this is where you can use principal component analysis to actually work in, to actually help you to understand your data. There's a question my colleague typed in the chat. I'm also concerned. What procedure should you do first before going for PCA? Now, my colleague is going to do some PCA analysis tomorrow. So we are going to handle part of this. There are issues there, like do I do principal component analysis based on a covariance matrix, based on a correlation matrix? For PCA, it's certainly you need that needs to be handled. For factor analysis, using hand may not really be much of an issue. Please, is the PCA form of regression? I think I've already answered this question. Please look at the presentation that we put in. I don't get a difference between principal coordinate and principal component analysis. I think principal coordinate is a form of multidimensional scaling. And in this case, the data is first converted into a distant matrix, and then the distant matrix is decomposed to produce dimension that you can then visualize like you do PCA. Somebody's saying, can we use Euclidean distance? Yes, there are many types of distance. Hopefully, when we're handling cluster analysis, we could mention a few distance measures. So you have Euclidean distance, you have Manhattan distance. If you're doing genetics, you have a lot more distant measures than you can imagine. Will you teach us a software for qualitative? No. Yes, multidimensional scaling is done in ARA, so you don't need to do it manually. Please, do you transform or standardize the variable before carrying out PCA? I think this one will be handled tomorrow. If you want to reduce data to a small size using PCA, how does it work? Do it sum of the several variables? Oh, we talked about this. I think we explained this earlier. These are all. So principal component analysis create new variables, which are linear combinations of the old variables. And those linear combinations, we just need to determine how many principal components are adequate. And then based on that, we can move on with the analysis. How does PCA in longitudinal data analysis and cross-sectional? Longitudinal, you have elements of time, and it can be useful, especially to reduce on the issue of multicollinearity. So it would actually be good for that. Okay, my question answered good. Do we direct? Most of the multivariate methods the presenter have talked about rely on visual presentation. It all depends on your interpretation for your visual representation, and that apart from the multivariate logistic equation that you can use p-value confident interval, is there any factual way one can present results or find, but that is not necessarily true. You can use, I mean, we have seen how to use p-value in determining the number of principal component or the number of factors to use. We talked about the Hotelling t-test yesterday. We talked about MANOVA. We talked about Mankova. all those ones uses they use statistical testing. So it's not just about visualization. Causes of forest degradation, such as firewood and that. Yeah, it's possible. Shall we be given certificate? Dr. Nyararo will answer that questions. For us, we are all interested in giving you the knowledge.
No.
I have dear forum. Thank you so much for the input. Been following. Okay, I think that one somebody else. I still have a challenge on how to export data table. That one. We're going to have another introductory level course. Why two-factor having two positive correlation and have one in negative? So it depends on the relationship that exists between the different factors and between the different variables. Can you generate significant level with correlation? Yes, certainly. Yes, after the factor loading or factor scoring, you can use the result from factor analysis to go and do regression. That is true. Can factor analysis be used for purely quantitative in science like experiment? Yes, you can also do that, but you need to be able to, it's all about whether you're able to interpret what comes out. Remember, the mathematically, you can get something very nice, but if you cannot explain it in terms of biology, then it might be an issue. No, there is no ideal for common variance. No. I'm not saying plant breeders should not use principal component analysis. I'm saying they should not abuse it. I think that is the big difference. You can use it, but don't abuse it. Supposing you have a lot of variables with factor one, how can you, I think this was answered. Okay, so I think, okay, I think we can and stop here. I thank you very much for your patience and dedication during the day. Maybe my colleagues have something to say, or I will take you back to Dr. Nyararo. So the ladies will, they refuse to let you listen to their voice today, but tomorrow they will talk to you.
Thank you so much, Dr. Dong, Dr. Namaweji, and Professor Tumuiwaze for today's session. Just wanting to respond to the question of certificates. We are not giving certificates this time. This session is meant to enrich your understanding of these statistical procedures using R. So it is just for your own benefit, not for the paper of the certificate. So thank you very much, everyone, for being here and attentive. For those who had the difficulties with their network, we advise you to visit our YouTube channel, and you'll be able to see these trainings there for your better understanding. Thank you very much. Have a good evening. Bye. See you tomorrow.
Okay, so thank you, everyone. Have a nice evening.